Okay, good day to everybody who's joined us, and I hope everyone is keeping safe and well in these uncertain times. Today, I want to talk about electrochemical corrosion rate measurements. So I'm going to talk about the theory behind the measurements that you can do, as well as focus on a couple of techniques, including polarization resistance, the electrochemical frequency modulation technique, and electrochemical impedance spectroscopy. So let's jump straight in to the theory. So corrosion is an electrochemical process involving electron transfer. This makes electrochemical techniques ideal for corrosion measurements, and a wide range of techniques have been specifically developed and standardized. And in general, they are both fast and sensitive, although fast is a relative term. Corrosion is inherently a slow process, where a typical corrosion rate can be something like 10 milliinches or 10,000ths of an inch per year. And the gold standard for corrosion testing is weight loss measurements, but these can take days, weeks, or months, or even years to make to get results. In electrochemical techniques, we're going to accelerate that process through polarization, leading to results in minutes or hours. Low corrosion rates are easily measurable with modern potentiostats, making electrochemical techniques very sensitive. This is because a low corrosion rate translates to a low current. And an example of that is if we take a 1 centimeter squared sample of iron with a corrosion rate of 1 milliinch per year, we're going to expect a current in the order of 2 to 5 microamps, which can easily be measured by a modern potentiostat. Electrochemistry, here's a review of electrochemistry. Electrochemistry is the study of chemical reactions accompanied by the exchange of electrons. Oxidation is the loss of electrons, and reduction is the gain of electrons. And oxidation we also call an anodic reaction, and reduction a cathodic reaction. So the dissolution of a metal is an example of oxidation, in this case the dissolution of iron, and the generation of hydrogen gas is an example of reduction. So in general, an oxidized reactant gains electrons to become a reduced product. The oxidation half reaction is usually the metal being tested, and the reduction reaction is some solution species. In corrosion, both these reactions are occurring on the surface at the same time, to a lesser or greater extent. Let's move on to the terms that we use for evaluating corrosion experiments. The first one is potential. Potential is the driving force for the redox reaction and is related to the thermodynamics of the system, which indicates if a reaction will take place or not. The potential scale is a relative scale, so that we always measure potential with respect to a reference point. And we need to remember that in general, there's no correlation between the thermodynamics of the chemical system and the kinetics of the rate of reaction. So we can measure whether the reaction will take place, but that doesn't necessarily mean it will. Current is a measure of the electron flow, which tells us the rate of reaction, essentially the number of electrons per second. The sign of the current also tells us if oxidation or reduction is occurring. An analogy to a potentiostat system is a closed loop water system where the pump is the potentiostat, the water pressure is the potential, The flow rate is the current, and the pipe restriction is a mimic of the corrosion reaction. Varying the water pressure via the pump will vary the flow rate. Corrosion experiments in general are not conducted at high voltages. 95% of them are within plus or minus 2 volts of the saturated calomel reference electrode. But the range of currents that we need to measure is quite large, could be over to 12 or 13 orders of magnitude. And modern potentiostats with the order ranging capability can measure currents over these wide ranges quite easily. Electrochemical techniques can be divided into active and passive experiments. Active ones involve applying an excitation to the system and measuring the response. For potentiostatic experiments, this involves controlling the potential and measuring the current, whereas conversely, galvanostatic ones involve controlling the current and measuring the potential. Passive experiments just observe a corroding system, which could involve measuring the potential, as in open circuit potential measurements, or for instance, a pH meter, or monitoring the current flow in the case of galvanic corrosion or electrochemical noise type measurements, where we use a zero resistance ammeter experiment. Active experiments in general are faster, but risk changing the sample. So potentiostatic experiments are the most commonly used because of the relationship between potential and thermodynamics. A potentiostat can control the potential between the sample and a reference electrode and measure the current between the sample and a counter electrode. The reason for using a 3-electrode system is because we can isolate the current voltage behavior of the sample to get more information that way. During the electrochemical experiment, we change the potential in some systematic way and measure the current response. So here's several examples of a 3-electrode cell setup. In the top one, we're going to, we'll see that the working or sample electrode is a kind of cylindrical sample. And in the bottom one, it's a flat sheet. Our reference electrode, and this is the sample that we're going to measure the corrosion rate of. The reference electrode could be one of either a saturated calomel reference or a silver chloride. And our counter electrode should be some kind of inert material, could be either graphite or platinum. So the open circuit potential is the potential difference between the sample or working electrode and the reference electrode when immersed in electrolyte. It's what we call a mixed potential because the value is determined by the potentials of at least 2 half reactions. It is independent of the potentiostat. And it's the starting point of virtually all electrochemical corrosion experiments. No measurable current flows at the open circuit potential, but a voltage applied voltage positive of the open circuit will accelerate the corrosion reaction, oxidation or anodic reaction, and a potential negative of the open circuit potential will accelerate the reduction reactions. So experiments like polarization resistance, electrochemical frequency modulation, EIS are designed to measure the rate of uniform corrosion. The corrosion current is measured, from which the corrosion rate can be calculated. These techniques yield an instantaneous corrosion rate, which can be compared to the average rate from a weight loss experiment. Although there is no measurable current at the open circuit potential, we know that corrosion is occurring. The half reactions are in dynamic balance, like walking up a down escalator. We need to measure the corrosion current, I core, which is the current due to either the anodic or cathodic half reactions. I want to give a quick aside to the precision of electrochemical corrosion measurements. Corrosion is a surface process involving a large number of variables. A relative standard deviation of 15% is excellent. This can be improved by increasing the number of replicates that you make, as seen in the graph on the right. The surface of the metal sample is highly heterogeneous with anodic and cathodic sites, and it's the interaction of these sites that leads to corrosion. The potentiostat itself is very accurate, so the accuracy and precision is dependent on the very dynamic system. So electrochemical corrosion measurements are based on good solid science developed over many years. I want to briefly touch upon the theory behind these types of measurements. So the principle of the theory that we use for looking at corrosion measurements is called the mixed potential theory. Principle of charge conservation requires that there must be at least one reduction and one oxidation reaction going on in balance. The graph, known as an Evans diagram, shows the current voltage behavior of interacting anodic and cathodic reactions. Here we have the generation of hydrogen gas, and here we have the dissolution of zinc metal. Because of charge conservation, the corrosion potential and current are indicated by the point where the lines cross here. So we can get the corrosion current from that point where they cross and the corrosion potential. The lines on the Evans diagram are dictated by the Butler-Volmer equation, which is a general electrochemical equation describing the relationship between potential and current. The total current is the sum of the anodic and cathodic currents and is related by the corrosion to the corrosion current by this exponential expression. Here we have a graphical representation of the current voltage relationship for a mixed potential system. This is in general termed the Tafel plot. The equation only holds for charge transfer controlled rates, and complications arise if there is passivity due to oxide layer formation, for instance, diffusion control, also called concentration polarization, which may be the diffusion of reactants to the surface or products away from the surface. We're also making the assumption that there's one oxidation and one reduction reaction, and alloys can complicate this situation. The polarization resistance experiment is designed to determine the polarization resistance, RP. The Stern-Geary relationship describes the relationship between the polarization resistance and the corrosion current. This relationship is a linearization of the Butler-Volmer equation, assuming that the ratio of the current, the voltage change that we apply to the surface over the Tafel constants is less than 0.1. Hence, the polarization technique uses an applied potential of not more than 10 or 20 millivolts away from the open circuit potential. The plot of potential versus current that we're going to get is approximately linear in this region. So let's look at the polarization resistance experiment. The experimental procedure for this experiment involves measuring the open circuit potential and allowing it to stabilize, then applying an initial potential 10 millivolts or maybe even 20 millivolts negative of the open circuit potential. And then we're going to slowly scan the voltage at a rate of about 1.125 millivolts per second, for example, to the final potential, which is going to be 10 or 20 millivolts positive of the open circuit potential. We measure the current and we're going to plot potential on the y-axis and current on the x-axis. And the reason for doing that is that when we measure the slope, the units of the slope are resistance. We can then convert that resistance or polarization resistance to corrosion current using the Stern-Geary relationship. And once we have the corrosion current, we can convert that to corrosion rate. So here's an example of a polarization resistance experiment, and we can see that in the region around where the current passes through zero, we have a linear response, and we can draw a straight line through that response to get the resistance, the polarization resistance for this sample. So to calculate I core from the polarization resistance, we're going to use, as I said, the Stern-Geary equation. We get the polarization resistance from the polarization resistance graph, and we can use knowledge of the beta constants, which perhaps are measured from a separate experiment using a Tafel plot, to calculate the corrosion current. We have to make sure that we use include the electrode area, as the current that we're going to measure is obviously going to be larger for larger surface areas. So to calculate the corrosion rate from the corrosion current, we're going to use Faraday's law. So we have this expression for charge is dependent on the number of electrons in the reaction, the Faraday, which is a constant, the mass of the mass loss, and over the atomic weight. So if we rearrange that equation to get the mass change, we're going to get a corrosion rate in grams per second, and we're going to substitute the atomic weight for this equivalent weight, which is can be used to calculate the atomic weight based on the alloy content of your sample. In general, we want to know, from an engineering standpoint, we want to know the corrosion rate in terms of units of penetration, so inches per year or millimeters per year. So we're going to divide both sides of the equation by the area and the density, and we end up with an expression like this that's going to give us the corrosion rate in either milli-inches per year, which involves the I core, which we've measured, the density, and the equivalent weight, which we can look up or calculate. So if we use the Stern-Geary equation to calculate the corrosion rate for this particular sample, we end up with a value of 6.07 milli-inches per year. And we need to remember that number because we're going to compare it with the two other techniques I'm about to talk about. So now to move on to the next technique, which is the electrochemical frequency modulation technique, which is a technique where you apply two sine waves simultaneously of equal amplitude. As with most corrosion techniques, it is centered on the open circuit potential or the corrosion potential. The applied frequencies need to be relatively prime, so that they don't share any common factors. And I'll point that out later when I give an example. The frequency chosen has to be slow enough to minimize current due to the capacitive behavior of the sample. And the size of the signal is chosen so that it is a non-destructive technique. So we can write the applied signal in the form of two sine waves, as shown in the initial, in this equation here. And the corrosion reaction behaves in the same Butler-Volmer fashion as we have seen for the polarization resistance experiment, where we assume activation control or kinetic limitation. But we will look at, we're going to be looking at the slightly non-linear region on the edges of the experiment. So I've written down the Butler-Volmer equation one more time just for example. So let's simplify the equation by calling the two frequencies A and B, and we're going to invoke a Taylor expansion of the exponentials up to the third term, which gives us a complicated equation with sine squareds and sine cubes. So this is a Taylor expansion. So we have an exponential and we can approximate it using this expression, which is also the same expression that is used to approximate in the polarization resistance experiment, except we only consider the first term. I'm not going to write out the complicated expression with sine squares and sine cubes. All I'm going to say is that we're going to use trigonometric expressions like the ones that I show to simplify the equation so that we end up with just terms in terms of sine and cos. And once we've substituted those trigonometric expressions, we're going to end up with an expression like this. And it eliminates, as you can see, it eliminates the sine squared and sine cubed terms. And we only have sums and differences of the frequencies that we have applied. So we have sums, differences, and also harmonics at 2 and 3 times the size of the original applied frequency. And there, each of these expressions has a constant, which are the amplitudes that we're going to see at each of the frequencies. And when we have sums and differences of the frequencies, we call those intermodulation frequencies. So as an example, when we substitute 2 and 5 hertz into the equation for the frequencies A and B, we end up with a table showing the frequencies that we're going to see responses at. So as you can see from the table, when we calculate these are all the frequencies in the expression that I showed previously. And when we calculate what those correspond to in terms of a real number, when we use 2 and 5 hertz, we can see that there's a range of frequencies, but none of them are duplicated. And in fact, we're going to get responses at these frequencies, and then we would expect the amplitude at those frequencies to be the same. And if you take note, we can also see that there are some gaps. So we don't have a frequency response at 11 hertz or 13 or 14 hertz. So that's what we should see when we to validate that the actual technique is working. So here is a representation of when we perform the EFM experiment, for the current versus time and voltage versus time plots. They going to look something like this. One thing to note is that the applied signal is repeated approximately every 1 second. So we're looking at here 5 repeated applications of the signal, and we do that so that we can average over a number of cycles to get a better signal to noise ratio. Then what we do is we're going to transform this time domain data into frequency domain data through a fast Fourier transform, and we end up with a spectrum that looks like this. And one thing I want to point out about this spectrum, we call this the intermodulation spectrum. So we got the responses at the different frequencies that I showed in the table. And here you can see that here's the fundamental frequencies that we applied. So we've got equal response here at 2 and 5 hertz. And then we've got equal size peaks here and here. And this one and this one are the same size. And then this one, and this one. And then these two here. And you can also see, as I pointed out, that there are missing responses at the points where we would expect not to see any response. So here, from the amplitudes of the different responses, we get we can give an expression for what those amplitudes should be in terms of I core and the beta constants. So we can get out I core, beta A, and beta C. And one of the things to note is that we can use simultaneous equations to calculate the different values. And one thing to note would be that I core, we get I core out directly without knowing the Tuffle constants. But in addition, we do actually get the Tuffle constants. In addition to the I core, an internal quality check can be made by ratioing the amplitudes of different harmonic and intermodulation peaks. So if we look at the ratio of the D and B peaks, we're going to get a value of 2. And so we ratio these two expressions, we're going to get a value of 2. And if we ratio the E and C peaks, so we're going to ratio these two, we get a value of 3. And these are sort of independent internal checks to see that the experiment is working correctly. So if we look at the spectrum of the same carbon steel that we did with the polarization resistance in the same solution, we're going to get this kind of response. And again, you can see that we get equal responses at the fundamental frequencies, and these two are the same, these two are the same, and these ones are approximately the same, and then the same here. And if we do the calculation to work out I core and the beta constants, we end up with a result like this. So if you remember the previous result, we got a value of 6.07. In this case, it's a little bit higher. We got 7.4. But we also see that these the values of 2 and 3 come out quite nicely, close to the values that they're supposed to be. So moving on to the third technique that I'm going to talk about, which is electrochemical impedance spectroscopy. I'm not going to give a detailed overview of the electrochemical impedance spectroscopy technique. If you want that, you can look at a previous webinar that Dr. Jacob Ketter has already given, which is on our website, and he'll give you the detailed overview of what's involved in EIS measurements. And then I'm going to show you the results for this carbon steel. So we can imagine that a model for the surface of a metal surface is that of a circuit, and that comprises of the double layer capacitance of the surface, which is set up due to the potential of the surface, and the ions in solution, which are separated by a thin, small layer of water, which gives quite significant capacitance. And then the electron transfer models like a resistance. And then we also have a resistance due to the electrolyte between the sample and the reference electrode. And that gives us a model, a simple model for the surface of what's called a simplified Randall cell, where we have a resistor and capacitor in parallel. So if we look at the response that you would get for that kind of circuit, this is a plot. It's called the Bode plot, which is a plot of the modulus of the impedance against frequency on the Y1 axis, and then we also look at the phase on the Y2 axis, and we get a response where at high frequency we see the solution resistance or uncompensated resistance. As we lower the frequency, the capacitive part becomes active, and then at lower frequency we see the resistance, which is a sum of the uncompensated resistance and the polarization resistance. So we have a way of getting out the polarization resistance. This can also be represented in what's called a complex plane plot or a Nyquist plot, where we plot the real impedance against the imaginary impedance. And for this kind of circuit, what we're going to see is a semicircle, where the diameter of the semicircle is the polarization resistance, and the shape of the semicircle is related to the capacitance. So we can get all those three values out from this as well. The normal way to get the modern way to get the information out is to fit it to a model. So we can make this model, and we can do a least squared fit to the data and get out the results that way. So the criteria for valid EIS measurements is that they must be linear, stable, and causal. So linear means that they obey Ohm's law, so that the value of impedance is independent of the magnitude of the applied signal. So if we double the size of the signal, we double the size of the response. And if it's linear, that no harmonics are generated during the experiment. It's stable, so the system does not change with time and returns to the original state after we've applied the perturbation. And causal is that the response of the system is due only to the applied perturbation. So when we look at a linear system, we know that inherently electrochemical systems are not highly nonlinear. But what we want to do is we want to zoom into a small section of the curve by applying only a very small excitation. And that's going to essentially give us a linear response. And that allows us to do EIS, to do modeling of the data and to fit it to models. So when we look at the results for the carbon steel, that's the same sample that I showed for the previous two techniques, we end up with a Bode plot that looks like this. We can see that at higher frequencies, we can see the uncompensated resistance here. And then as we go to lower frequencies, the capacitive behavior of the surface is evident. And as we proceed to lower frequencies still, we see that the curve is flattening out to give us the polarization resistance. And we can model this behavior as you can, to pull out the results for the different values. So if we do that, we end up with for EIS, we end up with a value for the corrosion rate of 6.2, which is close to the 6 that we got for polarization resistance, and still lower than the EFM result. So we can actually use the beta constants that we got from the EFM result to calculate these values. That's how we yield the results that we got here. So that's all that I've got for the moment. Went a little bit quicker than I anticipated, but so I want to thank you for joining us today and listening, and I'll hand over to see if there's any questions.
Okay, thank you, David. Yes, we've had a number of questions throughout the talk, which is good, and we're trying to get to them. So I'm going to try to start with some general questions. Let me pull up what I have here. So a nice general question that could be applicable for a lot of people is, how do we choose the frequencies for EFM?
So what I said is that if you look at the EIS response for carbon for your sample, and then maybe not everybody has that, but you can see here that at the lower frequencies that it's flattening over and forming a plateau, and the EFM really needs to be made in this sort of low frequency region here, where the EIS response is flattening out. If you're going to make a measurement at higher frequency, you're going to overestimate the corrosion rate, because you'll have some amount of capacitive behavior that's going to be included in your response. So it's a trade-off really between how slow can you actually make the measurement and how long it takes, and getting results that are close to the ones you might get from other techniques.
Okay. Is there a particular advantage of EFM over these other techniques?
As I pointed out, you can get the corrosion rate out directly without knowing anything about Tafel constants. So from that point of view, it does have an advantage.
Okay. All right. Okay, I have another question. This is about polarization resistance. For the calculation of RP from an LPR measurement, is it correct to consider a linear part of the IE curve which is not at the origin but just a little bit after? In this example, it was some measurements in biological fluids result in a curve that begins to be linear right after zero current.
Yeah, I guess so. I mean, you want to find a linear region. In truth, a lot of the experiments don't exhibit that linear region around zero, so you're going to have to sort of do a draw a line that's a tangent to the curved part. It really applies to the point where the currents are small, so the point where you pass through zero. So, but if you have a linear region that sort of starts around zero on one side of the zero point, I think you can safely use that as your starting point or your tangent.
Okay. Let me see here. And again, to everybody, we're getting a lot of questions, and so we're trying to get through these. We do have plenty of time, so we'll try to get through these. For those questions that you do submit, please include your name and email address so that if we can't get to it right now, we will follow up with an email within the next day or so. Thank you. Okay. Let me see here. We're going to check in with my other co-hosts at the moment if they have anything they would like to pose. I know some have pasted into private chat with me, but Andrew, Jacob, or Jerome, do you guys have any questions that you would like to pose at the moment?
Yeah, I have one question here for you, David. Question is from Vina, and it is EFM for oxide-coated systems. Is that possible because they do not get resistance at low frequency at all?
So they have the same, I mean, that's the same problem that you have with EIS and with polarization resistance, that your response is really due to the capacitive oxide layer, not due to any corrosion reaction that's happening. So the same applies there. You can't really make a corrosion rate measurement in any of those cases.
Okay. Here's a more general question. Let me jump in then. Okay, so we can obviously get Toffel constants by EFM. Is there another general technique that you can use, or is there a general technique that you could use to measure Toffel constants?
So the other way to do it is the Toffel plot. But to do that, you need to scan the potential over a wide potential range. That's going to, which is now not a non-destructive technique. So there's, you can make the measurement once, then the only way to do it again is to re-prepare your surface to get it again.
Okay, and since we just mentioned preparing a surface, what role does sample surface pretreatment play in these measurements, and is there a recommended method for preparing your surface as far as hand polishing with a specific grit of sandpaper or something like that?
I think I don't remember exactly what, but in some of the ASTM standards, they definitely prescribe a certain amount of polishing. I think they say 600 grit or something like that, but I don't know, can't remember for sure. I have to look it up. But okay, yes, you know, you should start with a clean, polished, prepared surface.
Okay.
I have another question here about the open circuit potential. Before the system reaches steady state, measured open circuit can have a fairly dynamic response. Is there anything that can be learned or extracted from the curve?
I don't know what you can pull out from that. Maybe you guys have another.
Sorry, could you repeat the question, Jacob?
Whether there's any information to be gained from the open circuit potential curve prior to it reaching its steady state. And I will voice one little thing with it. The direction that the measurement moves tends to indicate whether or not you've got oxidation or reduction that is driving it. But in terms of whether or not it tells you anything about the system that is meaningful in terms of corrosion rates and how well it is getting protected from corrosion, the answer, I think, is no.
Well, because it's the interaction of two reactions, depending on the direction, that actually probably doesn't tell you much, because it could be that one of the two reactions is is increasing, or it could be that the other one is decreasing, in which case it could go either way, I think.
I think about that with regards to inhibitors. When you add an inhibitor, you can tell whether it's an anodic or a cathodic inhibitor based on
that's
the direction
correct.
the open circuit moves. But in that case, you know that the corrosion rate is decreasing. So that is, you do have that as a bit of additional information.
Oh yeah, I agree with you.
Okay. Let me look through some of these others. Oh, I do have, yes, as far as preparing the surface, the ASTM G180 does recommend 600 grit sandpaper. Thank you to Evan for that information. I had another question. Can we use EFM in a two electrode mode?
I mean, yes, you can use it. The problem with two electrode mode, and this applies to every measurement, is that you're measuring both the surfaces that are in contact with the solution. So you're measuring the corrosion rate or the current voltage behavior of both electrodes, and you can't separate out the two. So if they're identical electrodes, I guess you could do it.
Okay.
You just have to be careful about what you choose for your area, I guess, I think.
Okay. Now let me see here, since we're still in this EIS of carbon steel, this is a more general question, but maybe we don't have the time. How do you model the EIS results to determine the corrosion rate of the alloy?
So I mean, when you model any results, you've got to define the model, and the model has to have, I guess, two inputs. One of them would be looking at the actual data to get an idea of what the model should be, and then the other one would be only adding modeling terms that relate to your understanding of the physical behavior of the surface. So in the case of if we look at this kind of surface, if we're saying that there's one reaction going on the surface, and we have capacitance due to the double layer all over the surface, then that's the model that we have to pick.
Okay.
I don't know if Jacob has additional comments.
Not really. I mean, alloys, most alloys are created for the oxide film formation that serves a protective nature. Mark Erasm has done a lot of work using EIS to probe the nature of those oxide films. But that has more to do with the capacitance, yeah, basically.
Okay.
There's a question here, if there is a way to measure corrosion rate involving a galvanic couple.
I mean, you can do the biased ZRA experiment. I believe there's a a patent on that, maybe, or at least some papers. The problem with that type of experiment is the current may be dominated by one electrode over the other. So you're just sort of getting the corrosion rate of the couple.
Okay. Just everybody, I'm getting some very specific questions. So a lot of these, we're going to have to follow up individually after the webinar. So do we have any more general questions to my fellow co-hosts? Okay, then let's stop here. I think this is a good stopping point. You know, we have all of your contact information, and we can follow up there. We did record this today, and so we will make it available. We will also make the PowerPoints, the slides available as a PDF, and send those out to people. We have a number of we have some more webinars organized, so take a look at our webinar page and register for those if you have any interest in those particular topics. And so anyway, I just want to thank everybody again for attending today, and be safe and stay healthy, and we'll see you next time. Thank you.